Welcome to Empowered Learning. This video will be about one of the applications that we use for definite integrals, and that will be to calculate arc length. Specifically, if I wanted to take some function and measure the length of that particular function from one x value to another, I could use the arc length formula that we're going to discuss in this video to do that. Now, the first thing that we're going to do is take some time to see how do we actually get this formula, and I'll show you what the formula is, and then we'll apply it to a few examples. Now, if we start off here, if we just wanted to find the distance between 2 points, we could easily just do that by using the distance formula here. Okay, and of course, most of us, we already know how to do that. However, if we had a situation where, let's say we had a particle that was going along a path, and the path of that particle is follows a lot like what this function does here, then of course it wouldn't be so simple to just use distance form, because again, the shortest distance in between 2 points is a straight line, and as you can see here, f of x is not a straight line. So we would have to find another way to do that. Well, it turns out that if our measurement tool that we used was small enough, we could essentially have a number of very, very small lines that we could use to just kind of go all on this function like this, all the way till we get to from x equals a to x equals b. And if we could add up all those very, very small lengths, then that essentially would be what the length of that particular function would be. Okay, so that's basically the approach that we take to be able to come up with the arc length formula. Now, I'm actually going to talk you through it and kind of show you how we end up with the final result. And I won't take too long to do it, but I feel like you do need to at least understand how we arrive at this formula before we start using it. So if we wanted to estimate the length of the path of, let's say, this particle traveling on f of x from x equals a to x equals b, we see that we have these divisions that we could do. Okay, and each division here would be a length of delta x sub k. And what I mean by that is, let's say if we zoom in on one of these, let me go back up here. Yeah, so this is the one that I want to zoom in on. So let's say we zoom in on, oh, pen is going crazy here. So let's say we want to zoom in on this situation here where we have the L sub k, okay, right here. So if we do that, then we see figure B sort of denotes or gives us an idea of what's going on. Now, if we zoom in there, of course we see that we have this length L sub k, which is not exactly the length of what our function is from x sub k minus 1 to x sub k, but if we're zoomed in really, really close, it's a good approximation. Okay, so from that, we also see that we can form a right triangle here, and we could use what most people know as Pythagoras Theorem, even though Pythagoras didn't make it up. That's what it's known as. We see the relationship in between the three sides of a right triangle, and of course we could use that to come up with the distance formula. Okay, so to find the hypotenuse, we just do the square of the change in the x values plus the square of the change in the y values, and we take the square root of that. Okay, and so that is what this particular length L sub k would actually end up being for that small piece. So now if we go back to figure A here and we say, all right, well, I have a way of being able to express my this length here, L sub k, in terms of the change in x over the change in y. I could do that for all of these lengths, L1, L2, all the way up to Ln if need be. Okay. Now the thing is to get the exact length of this curve from x equals a to x equals b, one of the things I know that would have to be at least theoretically true here is that n would have to approach infinity, meaning the number of these small links that I would use here to be able to measure the actual length of this curve from x equals a to x equals b, I would have to have an infinite amount to theoretically be able to measure the exact length of that curve from x equals a to x equals b. Okay? Well, it turns out here that since our function f of x is smooth and continuous along this interval from x equals a to x equals b, okay, and specifically, if we look at it from a micro point of view, we know that our function is going to be smooth and continuous from x of k minus 1 to x of k for any specific length L sub k. So we'll look at it this way. So for this closed interval here, let's try to get the pen acting right here. Let's try that again. Right, so for this closed interval here, we see that our function f of x, which is what this is, will be smooth and continuous. Okay. Now, since it's smooth and continuous, one of the properties that it has, and this comes from like a Cal 1 or Cal A course or your first year calculus course, is that a function that is smooth and continuous along a closed interval is also continuous and differentiable. Okay. So because our function is smooth and continuous, which means that it's also differentiable, we know that there's something called the mean value theorem that basically guarantees that if we pick some value c sub k, and that would be a value in between x sub k minus 1 and x sub k, if I pick some value there, the mean value theorem guarantees that the derivative of this function at c sub k, and if I was to look at that in a different way, and let me switch colors here for a second so that we can actually see this a little better. So if I have c sub k here, that means I would have this point on this graph, which means I would have this particular tangent line. And of course, the slope of that particular tangent line would be what the derivative of that function would be. And what the mean value theorem guarantees is that the derivative of this particular function at this value, c sub k, there is a value in between here and here that's that the derivative or the slope of the tangent line is going to match the slope of the secant line from x equals k, x of k minus 1 to x of k. And so what that looks like here is this. And again, this is just really a really fancy way of saying that the slope of the tangent line at c sub k is going to be equal to the slope of the secant line from x sub k minus 1 to x sub k. Okay. Now, we know that since that's true, we know that f of x sub k minus f of x sub k minus 1, that's just the change in the y values here. And of course, x of k minus x of k minus 1, that's just the change in the x values, okay, for this small piece here. So because of that, we know that we can take this situation here and rearrange it to where now, and I'm going to write this over here, that we could express the change in y sub k. Let's make that a subscript. We can take the change in y sub k and just rewrite this as the derivative of the function f evaluated exactly at a value c sub k times the change in x sub k. And so the reason why this is important now is because we now have a way of expressing the length of this very small piece of our function here in terms of purely just x sub k, because I could take what this is here and express it as derivative of f evaluated at c sub k times the change in x sub k. So I could do that. And so by substituting in that result, that's going to allow me to be able to now rewrite this length just in terms of the change in x sub k, and then that's going to eventually allow me to come up with what the formula for arc length is. And so we're going to talk about that next. So like I stated before here, this is stating the mean value theorem, and this is rewriting the change in the y values, y sub k, for that little small piece in terms of the derivative and just a change of x sub k. So if I go ahead and take this and I substitute it in, you see that I'll get what this result here is. And if I square both terms, I will have a common factor of the change in x sub k, quantity squared, that I'm going to factor out. And then, of course, if I take the square root of this squared, that's just going to give me the change in x sub k. And, of course, what I'll have is square root of what's left in here. Okay. Now, that means that this one very small piece or length that I'm using to approximate the distance, or the distance of the length of my function for that very small part, can be looked at like this. Now, note that there are a bunch of these very small lengths that I'm using. Okay. And so what I need to do is I need to add n of these lengths together. Okay. And of course, if n is approaching infinity, then that's going to come up to be what's called an infinite sum. And if I want to study the behavior of what all these lengths are going to act like if I add them up together, then that's actually going to be the limit of a Riemann sum. Okay. And of course, a Riemann sum is just this sum here going from k equals 1 to n. So basically, I'm just saying, hey, I got a bunch of these little things I need to add together, and I got n of them. And of course, the infinite sum would be as n approaches infinity, and that's where the limit part comes in. So if we do that, then of course you see, if I find out what's going to be the behavior of this sum as the number of these very small lengths I use to approximate what each small piece of my function length is actually going to be goes to infinity, I end up with this expression here. Now note that by definition, we take the limit as n approaches infinity and the summation part, and that is essentially what our integral sign is. Okay, it's a combination of those two things. And since we're looking at the length of our function from some value x equals a to x equals b, then we make it a definite integral. Okay, and then of course, by definition of what the integral actually is, we know that this delta x of k just ends up being dx, because it's essentially the change in this as x goes to 0. And this is the differential saying, hey, the smallest possible change in the x values. And then of course, here the c sub k, we would just write that as x because it is just some x value. And so from that, we eventually see here that the arc length formula is just simply our length is just going to be the definite integral from x equals a to x equals b of this particular expression here. And of course, we could express the derivative of the function x in its Leibniz form as dy over dx. And of course, we could use this as long as we know that what the derivative of the function is, and we know that the function itself is going to be continuous on this closed interval. Now, if we were to have a function x that was defined in terms of y, then the arc length would look this way. And the only thing that's really different is that, of course, now your limits of integration would be y values instead of x values, and you would have the derivative with respect to y instead of with respect to x. Okay. All right, so now let's get into doing some examples. So for our first example, we want to find the arc length for the curve 2 times x raised to the 3 over 2 on the interval from 0 to 8, and we want to integrate with respect to x since y is a function of x. So the first thing that we need to do is just make sure that we remember the actual formula. And so of course, arc length is going to be the definite integral from x equals a to x equals b, square root of 1 plus, and we're going to take the derivative of this function and then square it. And of course, 1 plus the derivative of y squared dx. So that will be our formula for that. Now, make sure that whenever you take the derivative, that you don't take the derivative, you don't try to take the second derivative. Okay, that's not the same thing. So you need to take the derivative, and whatever that is, you square that. Okay, so first thing we need to work on is figuring out what the actual derivative of y with respect to x is. So the derivative of y with respect to x would just be the derivative of 2x raised to 3 over 2. And of course, we can just ignore the constant. And then for the derivative of x raised to 3 over 2, that would just be 3 over 2 x raised to the 3 over 2 minus 1. I'm going to write 1 as 2 over 2. So these 2's reduce to 1. So we just end up having 3 here. And this will be 3x raised to the 1/2, which is just the same as 3 times square root of x. So that is what our derivative of y with respect to x is. And so this implies that if we take the derivative and we square that, then that's like me taking 3 squared, which is 9, and the square root of x, and squaring that, that's just going to be x. So now we know what the derivative of y with respect to x squared is. So therefore, the length, arc length from 0 to 8, because this should be what a is, and that should be what b is, where we start and where we stop. Integral of 1 plus 9x, square root of all that dx. And so now we're here, then this is just regular integration from Cal A. So to be able to work this out, we need to do substitution here. So we're going to let u be 1 plus 9x. And that means that du over dx, if I take the derivative of that, will just be 9, because the derivative of any constant is 0. Derivative of 9x is just 9. And of course, what that means for me is that 1/9 du is equal to dx. Okay. Since we have limits of integration here, we might as well go ahead and substitute that in as well. So also, we know that u of 0 is going to be the same as 1 plus 9 times 0. And that slipped there. And so that will be equal to 1. So that part is 0. And we know that u of 8 is going to be 1 plus 9 times 8. And that will give us 73, since 9 times 8 is 72. So now that we have all that together, we can rewrite everything for this definite integral in terms of u, and then figure out our answer here. So now the length is going to be from u of 0 to u of 8, square root of u, and in place of the dx, we're going to put 1/9 du. So let's write that, times 1/9 du. And this will just be 1/9 integral from 1 to 73. This will be u raised to the 1/2 du. And then we just take the antiderivative of u raised to the 1/2. And of course, if we do that, it's going to be u raised to the 1/2 plus 1, which we'll write as 2 over 2, divided by the same. And that will be evaluated from 1 to 73. And from here, we'll just carry out the calculations moving forward there. And let me go ahead and change this right quick, because that doesn't look too hot. Yeah, so that looks better. All right, so this will be 1/9. On the inside here, we know that our denominator is going to be 3 over 2, which will be 2 over 3. And we will have u raised to the 3 over 2 here. We'll evaluate that from 1 to 73. All right, and so this will be just 2 over 27. U raised to the, and I'm actually going to put this in radical form now. So this will be the square root of u cubed. Go from 1 to 73. And square root of u cubed is just going to be u times square root of u, from 1 to 73. And I'm doing all this extra stuff so that when I actually plug in 1 and 73, it'll be relatively easy for me to do. So now at this point, got 2 over 27, and I'll have 73 times square root of 73 minus 1 times square root of 1. All right, and so at this point, we pretty much have the answer here, because we know that 1 times square root of 1 is just 1. So we'll just say 2 over 27 times 73 times square root of 73 minus 1. And if we round that, that's going to be roughly, and this is what I get from my calculator here, 16.12683507 units. Okay. And so this is your exact answer. And of course, this is your decimal approximation. And so depending upon what you're required to do, you may or may not need to give the decimal approximation, but I think it's always good practice to calculate the exact answer. Okay. All right, so let's move on to the next example. Okay, so for our second example, we want to find the length of the curve defined as x is equal to 1/5 of y raised to the 5 plus 1 over 12 y raised 1 over 12 y cubed. And we want to do that from y equals 1 to y equals 2. So one of the things that we see here is that our function is defined in terms of y instead of in terms of x. So we need to use the arc length formula that tailors to that. So here we know that arc length will be integral from c to d in this case, square root of 1 plus derivative of x with respect to y, square that, and then dy. So just like how we did before, the first thing we need to do is figure out what the derivative of x is in terms of y. So we say dx over dy is going to be the same as taking derivative of what we have here. And I'm just going to go ahead and rewrite 1 over 12y cubed. It's just 1/12 of y raised to the negative 3. So if we take the derivative of the first term, we're just going to get 1/5 times 5y to the 4 plus 1/12 times a negative 3 y raised to the minus 4. Okay, using differentiation rules, and that simply simplifies to y raised to the 4 minus 1/4 y raised to the negative 4. We know that because it's negative 3 and 12, that reduces to negative 1 here and 4 there. So now that we know that, then this tells us here that the derivative of x with respect to y squared is just going to be y raised to the 4 minus 1/4 times y raised to the negative 4 quantity squared. And of course, this is going to follow the profile of a minus b quantity squared, which is just going to be a squared minus 2ab plus b squared. So we're going to follow that. And thus we end up having y to the 4 squared minus 2 times y to the 4 times negative 1/4 y to the negative 4, and then plus have 1/4 y raised to the negative 4 squared. And of course, we'll work that out and simplify that. So what this ends up being, once we're done here, is this will be y raised to the 8th. This y raised to the 4 and this y raised to the negative 4, if we multiply those together, that gives us y raised to the 0, which is just 1. So what I'll do here to notate that is we will say this and this reduced to 1. And of course, this negative times the negative, let's see. Oh, yeah, that negative shouldn't be there. So let me get rid of that because we're doing b, and b doesn't include the negative there. So here we see that our 2 and 4, 2 divided by 4 just reduces to 1/2. And so we just end up with a negative 1/2 here. So this will be minus 1/2. And then our last term ends up being 1 over 16 times y raised to the negative 8. And so that will be our expression that we'll put here for the derivative of x with respect to y squared. Okay. Now, one thing I do want to go ahead and mention here is that we want to pay close attention to the fact that this y raised to the 4 minus 1/4 y raised to the negative 4 quantity squared is equal to this. And we want to do that because we may actually see that pop up again as we work in this problem. And by knowing what we're seeing now, that'll help us to cut down on some of the work that we'll need to do later. Okay. All right, so we're going to make this 8 look a little better, and then we'll go ahead and move forward here. All right, so therefore, we know that the arc length is going to be, and since we're going from y equals 1 to 2, we know that these will be our limits of integration, square root of, and this will be 1 plus, and now we have to write all this business in, y raised to the 8th minus 1/2 plus 1/16 y raised to the negative 8. So you have all that, and then that's dy. And let's not do that yet. So now that we're here, we just need to simplify the radicand. So we're going to do integral from 1 to 2. And we know that this 1 minus 1/2 is going to be just a positive 1/2. So let's say y raised to the 8 plus 1/2 plus 1/16 y raised to the 8 dy. Okay. Now, at this point, notice that what we have here in our radicand looks very similar to what we have right here. Okay. The matter of fact, the only thing that's different in it is the fact that we have a minus right here instead of a plus. And so because of that, what that lets us know here is that this is following the same pattern as this a minus b quantity squared, except for now that minus is now a plus. So here, this is following a plus b quantity squared. Oh, well, sorry, this is down here. So let me erase that. So what we have going on over here is that this is following the pattern of a plus b quantity squared, which would be a squared plus 2ab plus b squared. Okay. So saying all that to say is that now we could rewrite this y raised to the 8 plus 1/2 plus 1/16 y raised to the negative 8 as just y to the 4th plus 1/4 times y raised to the negative 4. And by doing that, that'll significantly cut down on some of the actual work that we'll have to do here. I'm going to erase that 1/2 because it wasn't looking too hot. So we got that a little better. All right, so now we'll just say this is the integral from 1 to 2. And we'll just rewrite this as y to the 4th plus 1/4 y raised to the negative 4. And all of that squared dy. Okay. So now that we have that, then the beautiful thing here is that we know that the square root of whatever's in the radicand squared just ends up being the absolute value of whatever the radicand is. So this would just end up being what we have here. And so now, one of the things that we need to know is from 1 to 2, is this particular function y to the 4th plus 1/4 y raised to the negative 4, is that going to remain positive or at least non-negative throughout the whole interval from y equals 1 to y equals 2? And it turns out that it does. So if you're wondering, well, how did you know that? Well, one way you can do it is just to graph it. Another way that you can do it is to kind of rewrite it and see that, no matter what you get in between 1 and 2, you're going to remain having positive values. So, but the thing is that in dealing with these integrals, whenever you come up on something like this, you really do need to verify that the function that's inside the absolute value sign is indeed non-negative over the whole integral. Okay. If it isn't, then of course you're going to have to break the integral up and account for the fact that, hey, some of this particular function is going to be below the x-axis here. Okay. Now, of course, for this one, it's relatively easy because we know y raised to the 4th is always going to have positive values because of how that graph looks. And of course, here, 1/4 y raised to the -4. Another way of writing that is like this. And the important part is this piece. And as long as y is greater than 0, we know that the graph of this particular function will be above the x-axis as well. So in short, just by me looking at it, that's how I know that that function will end up being always a non-negative from 1 to 2. So now that we've addressed that, we can go ahead and continue and just rewrite this as y to the 4th plus 1/4 y raised to the -4 dy. Okay. And so now from here, we're back to first year calculus, where all we have to do is take the antiderivative of both terms here and evaluate from 1 to 2, and then we will get our answer here. So the rest of this is just really computation from this point. So if I take the antiderivative of y to the 4th, that's going to be y to the 5th over 5. And essentially what it's going to end up looking like, it's very much like the function that we started with. Okay, won't be exactly the same, but it'll be very close. So we have 1/5 y raised to the 5, and then plus, ignore the constant, and this will be y raised to the -4 plus 1, which will be a -3, all over that same -3, and then we evaluate it from 1 to 2. And so we'll simplify a bit here. So this will be minus 1/12, or just 1 over 12y cubed. We'll do that from 1 to 2. And so now we just plug in 2 in for y first. So if I do that, that will be 2 raised to the 5 divided by 5 minus 1 over 12 times 2 cubed. And then we do the same thing with 1. And that should be a plus, not a minus. Oh, yeah, it should be a minus because of that. Yeah. All right, and so we'll do the same thing here. So this will be 1 raised to the 5 over 5 minus 1 over 12 times 1 raised to the 3. All right, and so from here is just sort of a race to the finish as far as calculations are concerned. So we know that 2 to the 5 is going to end up being 32. So this will be 32/5 minus, we know that 2 raised to the 3 is 8, and 12 times 8 is 96. So that will be our first two terms. Of course, 1 raised to the 5 is just 1 divided by 5, so that's 1/5. And this would be over 1/12, since 1 cubed is 1 and 1 times 12 is 12. Okay. All right, and so now from here, let's see. I'm going to go ahead and distribute this negative to both terms here. So we have that. So now I notice that I could regroup these. So I can put these two together. And then I could say plus 1/12 minus 1/96. And let's make that look a little better. Okay. All right. So now at this point, of course, we know that 32/5 minus 1/5 is just 31/5. So that is relatively easy. Okay. So for the 1/12, since we know that 12 times 8 is 96, we know that we could rewrite what we have here as just 8/96. So 8/96 minus 1/96 will end up giving us 7/96. This will be plus 7/96. And then from this point, we'll just figure out what the answer is the quick and dirty way, which is we'll say 31 times 96 plus 5 times 7, all that over 5 times 96. Okay. I could have found out what the least common denominator between, the least common multiple in between 5 and 96 would be, and use that to find the least common denominator, but I'm just going to do it this way. So 31 times 96, that ends up being 2,967 plus another 35, and all that over 480. And it ends up being 3,011 over 480. And so if you try to reduce that fraction, you'll see that you can't. So that ends up being your final answer. And of course, we will just put units here at the end because of the fact that this is a length. We were not given that it was in feet or centimeters or anything like that, but we do want to recognize that the answer that we're finding is some unit of length. All right, so let's look at our third example. So for our third example, we see that we have this equation, x raised to the 2/3 plus y raised to the 2/3 equals 8 raised to the 2/3. And this describes a graph of what we call an asteroid. Okay, and I've kind of done my rendition of what that actually looks like. I know it's not the best looking thing, but hopefully you get the idea. So we want to find the length of this particular asteroid by finding length of half of the first quadrant portion, which is characterized by this particular function, and we want to find it from x equals 2 times square root of 2 to 8. So essentially what we're trying to do is find out what the length of this is. And since this particular relation here, we're describing it as just a function from x equals 2 times square root of 2 to 8. We know that this particular shape here, even though I haven't drawn it that way, all of these lengths here should be equal to one another. Okay. So we find one, and then we know what the length of these other 7 are. 1, 2, 3, 4, 5, 6. I think I miscounted one. Yeah, so 2, 2, 2. Yeah, that one. I missed that one. So we have 8 of these all together. So if we find one, we just multiply our answer by 8, and that'll end up being what the actual length of this relation, better known as an asteroid, actually is. So we take the fact that we know what y is defined to be from x equals 2 times square root of 2 to 8. And actually, this is probably defined all the way up to x is equal to 0, but we're only looking at it for this one little piece here. So when we do that, of course, our formula is going to be, arc length is going to be integral from lower x value to higher x value, square root of 1 plus, take the derivative of y and then square it, and all that times dx. And so you see here, the very first thing we do is try to find what the derivative of this particular function is. So in looking at that, of course, the derivative of 8 raised to the 2/3 is just going to be 0, because the derivative of any constant will be that. But also notice that we have this 3/2 here. So this means that we're going to have to do the chain rule. So using the chain rule tells us that we have to take the derivative of the outside function first. So we look at all of this as just some big box, and we say, all right, what is the derivative of blah raised to the 3/2? And that's just going to be 3/2 times blah raised to the 3/2 minus 1. And of course, that'll give you 1/2 there. Now, the chain rule also says that once we take the derivative of the outside function with respect to all the stuff in here, we multiply that times the derivative of the inside function with respect to x. So we have to actually take the derivative of 8 raised to the 2/3 minus x raised to the 2/3. So, of course, for this portion, we just rewrite that. And when we take the derivative of the inside function, the first term, of course, will go to 0 because the derivative of any constant is 0. And then we'll use the power rule for x raised to the 2/3, which ends up giving us a negative minus 2/3 x raised to the negative 1/3. Okay. And so then from here, you see all we're doing is just simplifying. And so now I've simplified this and got it into a form that I could possibly use for my for this particular formula here. Okay. Now we just found the derivative, so we're going to need to square what we have here before we use it. So here you see that we put this result that we have here into our formula for the derivative of y with respect to x, which is all this business here. And of course, we gotta square that. And so, of course, in squaring it, we know that since this is multiplied, we will square the first factor times squaring the second factor. And so when we do that, of course, for the first factor, it ends up being x raised to the negative 2/3. For the second factor, since 1/2 times 2 ends up being 1, we just end up having 8 raised to the 2/3 minus x raised to the 2/3. Okay. And so from here, I'll multiply through by x raised to the 2/3. And we see here that for this first term, it just ends up being 8 divided by x, because remember, x raised to the negative 2/3 is just the same as 1 over x raised to the positive 2/3. And if I multiply that by 8 raised to the 2/3, then of course my exponential rules tell me that this is going to end up being just 8 divided by x, all that raised to the 2/3. Okay. Now, when we multiply that times the second term, we know x raised to the negative 2/3 times x raised to the positive 2/3. We add the exponents, and now just end up being x raised to the 0, which is 1. And so that's how we get that. So now that we're there, we see that, yep, this is going to start to simplify a bit. And before I move on here, I'm going to rewrite this here, just in case everyone's not following. I could rewrite this way because of my exponential rules. And so here, this 1 and minus 1, that will cancel to 0. And so all I will have left is square root of 8 divided by x, all that raised to the 2/3. Okay. And of course, square root of something is the same as that something raised to the 1/2. And of course, when I have something that looks exponential raised to a power, I can multiply the exponents, and I see that I just end up having 8 divided by x raised to the 1/3. And of course, this integral here I keep on carrying. This is a typo. I need to put an equal sign there. So yeah, forgot that, but caught it. So now from here, if I have 8 divided by x raised to the 1/3, I can just do 8 raised to the 1/3 divided by x raised to the 1/3. And of course, 8 raised to the 1/3 is the same as cube root of 8, which is just 2. And of course, x raised to the 1/3 is just x raised to the 1/3. And from here, I can move this constant outside of my integral, and I can move x raised to the 1/3 up to the numerator so that I can rewrite it as x raised to the negative 1/3. And so now from that point, it's just a matter of taking the antiderivative of x raised to the negative 1/3 and evaluating that result using the net change theorem from Cal A from 2 times square root of 2 to 8. And of course, in doing this, I know that this 2/3 in the denominator will be the same thing as 3/2 if I rewrite it, because basically we're saying the reciprocal of 2/3 is the same as 3/2. These 2's here will reduce to 1, and so I got 3, and I can rewrite this x raised to the 2/3 as cube root of x squared, and then from that point, just plug in 8 in for x, then plug in 2, make sure we subtract via the net change theorem, and once we do all that work, we see that all that ends up being 6 units here. So that means the total length of our asteroid is going to be 8 times that, which is going to be 48 units. Okay. So before we do our very last example, we want to go over how to compute the arc length for parametric equations. And so let's say if we have our variables x and y in this formula here for the arc length, where x is actually a function of t and y is a function of t. And of course, t is on some closed interval from a to b. And we know that both of these functions travel across this interval exactly once. And I don't know why this says 1. This should be once. As t increases from a to b. In other words, our parametric equations work together here to describe the actual function that we're talking about. So, and that will be the function y as a function of x. And so we're just assuming here that both y and x are tied to some function t here. So the whole point of that is to say that, hey, we may define this function, it really may be like a composition function. So that's another way of saying it. So anyway, so if we have all that together here, then we could use this particular formula to allow us to be able to figure out what is going to be the length of this particular parametric equation, which should be a smooth curve. Okay, so we're going to use that in our final example here. All right, so we want to find the length of the arc of the curve, x is equal to t squared, y is equal to t cubed, that lies in between the points 1, 1, and 4, 8. And parametrically, that would be on the interval from t to t, closed interval of t from 1 to 2. Okay, so we know here that the arc length formula for this situation will be integral from a to b, square root of the derivative of x with respect to t squared, plus the derivative of y with respect to t squared. Take square root of all that, and we will be integrating with respect to dt. Okay, so the first thing that we need to do is figure out, well, what is going to be dx over dt and dy over dt. Okay, well, we see here that since x is t squared, then that means that the derivative of x with respect to t is just going to be 2t. Okay. And we also see here that dy over dt, since y is actually t cubed, would be 3t squared. Okay. So therefore, we know that if we square both dx over dt and dy over dt, we are going to get 4t squared, and let's square this one, and we would get 9t to the fourth. So 4t squared and 9t raised to the 4 respectively. Okay. So now that we have that, we can now say the length of this particular curve is going to be the integral from, and of course, since we're taking the integral with respect to t, we're going to use these values here for a and b. It's going to be from 1 to 2. And we'll say square root of, and we'll have 4t squared here, plus 9t to the fourth there, dt. And so now all we have to do is just integrate this. So in working here, one of the things that we'll see is that we have in common t squared in both terms. So t squared there, and this will just be 4 plus 9t squared here, dt. And if we separate this, we know that square root of t squared, well, I'll just go ahead and write it. So this will end up being this times square root of 4 plus 9t squared, and all of that dt. And let's make that look a little better here. Okay. All right. So now that we have that, we know that square root of t squared, that is just going to be absolute value of t. So we'll go ahead and note that. This is just absolute value of t. And since t is on a closed interval that's always going to be positive, we're just going to just simply write that as t. Okay. So let me move down here a bit. So now we see we have integral from 1 to 2 of just t times 4 plus 9t squared and all that dt. Okay. So now all we have to do is just integrate that. Now, of course, we look at this and we say, all right, can't take the antiderivative of the integrand straight up, but we do see here that this 4 plus 9t squared, if I was to take the derivative of 4 plus 9t squared, I would get 18t. And the important part of that is t. So I would have a way to use substitution and rewrite this t times dt in terms of some other variable. Okay. So here what we're going to do is we're going to say, and actually let me switch colors here. So we're going to let u equal everything that is under the radical. Okay. So we're going to say let u equal this 4 plus 9t squared. And of course that means that du over dt, that's going to be 18t, which in turn means that 1/18 du will be equal to t times dt. And so that's our way of being able to replace the t and the dt here in terms of u. Of course, we can rewrite all of this in terms of u. So the only thing that we need to deal with now is changing 1 and 2, change that from being in terms of t to now being in terms of u. So also u of 1 is going to be equal to 4 plus 9 times 1 squared, which is 13. And u of 2 is going to be 4 plus 9 times 2 squared. All right, and so of course 2 squared is 4. 4 times 9 is 36, and 36 plus 4 is 40. So now we have everything we need to be able to finish up here. So I'm going to switch colors again. So therefore, this length is going to be integral. And instead of writing from 1 to 2, it is now going to be from 13 to 40. And we're going to have, instead of t times dt, we're going to have 1/18 du. And of course, instead of having square root of 4 plus 9t squared, we're just going to have square root of u. So this is what we end up having here. And of course, square root of u is just the same as u raised to the 1/2. So I'm going to go ahead and rewrite that. So that's u raised to the 1/2. And so now at this point, we just got 1/18. We take the antiderivative of u raised to the 1/2. That is going to be u raised to the 1/2 plus 1 over the same. We evaluate that from 13 to 40. And of course, this 1/2 plus 2/2 is going to be 3/2. But if we take the reciprocal of that, that's going to be 2 over 3. U raised to the 3 over 2 from 13 to 40. And 2 and 18, that'll reduce to 1/9. So we'll have 1/27. And then this u raised to the 3 over 2, we've already seen that before. That's just the same as u times square root of u. And we evaluate that from 13 to 40. And so now I'm just going to finish up here. So this will be 1 over 27. Substitute in 40 the first time. And then plug in 13 for the second time. In for u. All right, so at this point, we could do some simplification here, but it's really not going to profit us a whole lot to do that. So, I mean, I'll do some simplification here, but at the end of the day, it's just going to be what it is. So, and I'll give you what the decimal equivalent for this will be. And pen is dragging today. Oh, let's move that back. All right, so let's try to finish this up here. So I got 1 over 27. And of course, this square root of 40 here Of course, we could rewrite this as just square root of 4 times square root of 10. And so, of course, square root of 4 would just be 2. So this would be 2 times 40, which is 80. So the only thing we could really do here is just rewrite this as 80 times square root of 10. So that's about it. So we'll just say 80 times square root of 10 minus 13 times square root of 13. And then from there, that's about as simple as you can get it. Anything else, if we want the decimal equivalent, it's going to be roughly 7.633705416 units. And depending upon how much or after how many decimal places you need to round, you can make that number shorter. I just normally have a habit of actually writing everything that the calculator gives me, and then if I need to round, I'll go ahead and do that in my next step. So, but anyway, so you see here how we actually use the parametric form of the arc length formula to be able to figure out what was going to be the length of that particular curve. And so we've done 4 examples here. It's really not much to it to the arc length. As you can see, the hardest thing is just kind of getting through all the computation that you have to do once you get started. But the concept of arc length is actually pretty simple. So I hope that this video helped you navigate through these types of problems, and I hope to see you on the next video. Take care.